Oh, dearie me. Right, hello guys, we are live. We are live with George Hnatiuk, and he's having a few technical issues. We had it all set up, ready to go. I was waiting with him right there and then, and he's dropped the cam for the. How many times would you say you've dropped that camera now?
So it's a problem.
It's a problem. It's certainly a problem. But we're getting there. We're getting there. Hopefully, you're not going to touch any wires and knock anything. Hopefully, we can get this presentation underway.
Okay, am I coming through okay now?
You are, yeah, and everything seems to be squared up. You've got the pit. Oh, you've just nudged it.
I hit the wire again. Damn it.
Oh, dear me. This is quite funny. This is quite funny. Well, you are presenting. Sorry. Right, just try and avoid the wires again.
Yeah, well, once I get rolling, I'll be away from this.
Okay.
Okay, there we go.
Right. Right, so here we have George. He's going to do a presentation on gas pressure. Away you go, George.
All right, Randy, thanks. As Randy says, I've been having some difficulties here because I'm in another part of the house that I'm not used to using my setup, and so there's been a few logistic problems. What I'm going to do here is get into gas pressures and the gas law and discuss that and how to properly use it. There seems to be a lot of discussion lately regarding gas pressures and things. And before I get going on that, so to kind of get me warmed up, I'm going to talk a little bit about atoms and the periodic table. I was playing with the periodic table the other day, and I found some really interesting things out that I hadn't realized before, and it's not in any text anywhere. So I'm just going to talk a little bit first about atoms to get wound up, because this will lead into gases and gas pressures, that sort of thing. Most of you have probably seen the periodic table of elements, and this actually is probably one of the greatest discoveries of the human mind, really. This ranks right up there with Einstein's discoveries. This was first put together by a Russian chemist, Mendeleev, and there's a particular organization to the elements that comprise all compounds here on Earth and in the universe. You've all heard of atoms. Atoms are the very basic unit. If you take substances and keep dividing them, you'll get down to a fundamental level on which you can't really divide them anymore without losing the functionality of an atom. You'd have to start deconstructing the atom. Every element has a particular configuration that determines its properties. And the elements are the basic building blocks that we have for constructing compounds and matter here on Earth and in the universe. And there's a very specific organization on the periodic table, which is very, very clever and is related to quantum physics. Quantum mechanics perfectly explains the periodic table. So what we have going here is, let's first try to see where I'm at here. Talk about an atom. An atom is comprised of a nucleus, a center portion, which contains two particles called protons and neutrons. The protons are positively charged. The neutrons are electrically neutral. And about this nucleus, there's what we call an electron cloud. You've probably seen in high school or something where they describe the electrons orbiting the nucleus of an atom. Well, that's not an accurate description. That borrows from what is called the Bohr model, the first model of an atom. And we now know that the electrons don't have nice specific little orbits about the central portion of the nucleus. They describe more of a cloud. It's a probability distribution as to where the electrons reside outside of the nucleus. Now, electrons are negatively charged at the same magnitude as the protons. And the charge is 1.609 times 10 to the minus 11th coulombs. That's a very, very small charge. But a proton has a plus E charge in equal magnitude to the charge on the electron. They're equal and opposite and tend to cancel one another. Now, an atom is mainly empty space. If you look at the dimensions of an atom, typically the diameter of an atom is on the order of 1 angstrom. An angstrom is 10 to the minus 11th meters. Very, very small. Whereas the nucleus, if we were to look at the diameter of the nucleus, I'll call it dn, the diameter of the nucleus varies from 1.6 femtometers to about 15 femtometers. A femtometer is 10 to the minus 15th meters. So if the diameter of the atom is 10 to the minus 11th and the diameter of the nucleus varies between 1.6 and 15 femtometers, you're looking at the outside diameter of the atom where the electrons reside being about 1,000 to 10,000 times greater in size than the nucleus. So outside of the nucleus, it's mainly empty space. And the electrons just kind of reside in a cloud. Now, the electrons reside in various energy levels called shells. And these were first observed in X-ray absorption studies of an atom. And we now know with quantum theory in that why this occurs. And every electron has 4 quantum numbers associated with it. There are 4 quantum numbers called the principal, the orbital, the magnetic, and the spin. And every electron has to have a unique set of quantum numbers associated with it. This is called the Pauli exclusion principle, is that no 2 electrons within the same atom can have the same set of quantum numbers, that the quantum number set has to be unique for each electron. So you have the principal number called n. And that's what we have here on the periodic chart. These are your principal energy levels, are the rows. And this is your principal quantum number. And then you have the orbital, which we call L. And then there's the magnetic, called M, L. And then there is the spin, which is designated by MS. Now, the quantum numbers, like I said, are unique for each electron within an atom. The principal quantum number gives you the order of increasing distance that the electrons are from the nucleus. It tells you the electron distribution as a distance away from the nucleus. The orbital denotes a subshell within each shell that the electron can occupy. Within a shell, you can have many different types of subshells. And then the magnetic tells you which orbital within a subshell an electron can occupy. And then there is the spin value, which is either plus or minus 1/2. And like I said, this group of 4 quantum numbers is unique for any given electron within an atom. Now, the orbitals, or the shells and the subshells within an orbital, have different types of distributions. There is a subshell orbital called the S, which is, if you spin this around, you have like 2 spheres opposite one another, and you can have 2 electrons occupying that. And then there is the p orbital, or the p subshells, and within the p, you can have 6 places where an electron can likely reside. They look like dumbbells along the XYZ axis. And the electron isn't likely to appear between these distributions. This is where you're most likely to find an electron. And then there are more complicated, we can get into what's called the D subshells, and they have much more complicated types of distributions. Now, the amount of electrons, the number of electrons that can be occupying any given shell is given. The number of electrons is 2 times n squared, where n is the shell number. So in the first shell, we can have, let me shoot. Let's see. Well, in the first shell, we can have 2 electrons when n is equal to 1. And in the second shell, when n is equal to 2, we can have 8. And in the third shell, we can have n squared, which is 9 times 2. And we can have 18 electrons. So what we have is in the S shell, we can occupy it with 2 electrons. The P shell, when n is equal to 2, can have 8. Or not the P, but I mean the energy levels. So when n is 1, we can have 2. When n is 2, we can have 8. When n is 3, we can have 18. Well, what that means is that in the subshells, we have a subshell. An S subshell can hold 2 electrons. A P subshell can hold 6 electrons. And a D subshell can hold 10. And an F can hold 14. So what this tells us is that we're in the first shell. Along this row, we can have 2 electrons. So we can have hydrogen and helium. That occupies the first shell. Then when we go down to the next row, we're at the second level, the second energy level, and we can have a total of 8, which means then we fill the S2, 2 electrons in the S2, and then we have 6 electrons that can fill the P subshell. And the same thing happens on the third row here, is we can occupy a total of, we have 2 from the first. Remember, each element has to fill all of these shells as we go further down into the periodic table. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 when we get to argon. So we're at the third level. So we can fill the S shell, the 1s, the 2s, the 2p, the 3s, the 3p. And that gets us to argon, and so on. Now when we get to the fourth row, not only do we fill S shells and P shells, now we have 10 D shells we can fill up. So that's how the periodic table is structured, is how the electrons fill up the various subshells that surround the nucleus. So for example, if we wanted to look at silver, Ag, number 47 on the periodic table, but the periodic table keep in mind, is arranged by the number of protons that are in the nucleus. You count the number of protons in the nucleus, and then that determines the atomic number. So the atomic number for silver is 47. So that tells us there are 47 protons in the nucleus. And then to make it electrically neutral, we also have to have 47 electrons in a electron cloud about that nucleus. So for 47, what we do is we fill up the 1s, 1, 2. Now we're to helium, an inert gas. And then we fill up the 1s and the 2s, 1, 2, and the 2p. We have 6 electrons. That gets us to neon. Then at the third level, where we have the 2 1s, the 2 2s, the 2p, and now we fill up the 3s shell and the 3p. And then when we get to the fourth level, we fill up all those previous shells, and now we get to the 4s, and then we fill up 10 electrons in the d shell, and then we get to the p shell and fill it up. And then when we get to 4, we're at element number 36, which is krypton. So, well, let's look at what we have. The number of electrons is going to equal to the atomic number 36. So how does that work? So when we're at 4, the fourth level, 2 to 4 squared is 16 times 2 gives us 32. So that's where we are. Let's see here. 16, 32. What did I mess up on here? Pardon? Oh, okay. Let's see here. Okay, I hate to touch it. Let's see. For 16, 32. Well, what did I mess up here? Let me see. 1, 2, 3, 4. 32. Well, this is 418. I believe I did something. Isn't quite right. 1632. Well, I'll move on here. I'll get that figured out what I messed up here. Oh, crap. 418. 32. 2 10 squared. Well, anyway, let's see. Well, I'll move on here. The thing I found that was kind of interesting here the other day with the periodic table is keep in mind that the periodic table is arranged by the number of protons in the nucleus. And not by density as some people think. If you're to look at the periodic table, I don't know if this is this coming through okay where you can see the colors, Ranty? Okay, well, if you look at all the densities of the various elements in the periodic table, the green ones here are gases at room temperature. So all the gases are grouped together. The noble gases or the inert gases, the inert elements are always gases. They don't react with anything else. And then if we look at the densest elements, in the periodic table. They're grouped here. We have tungsten, osmium, iridium, gold, and platinum, and then uranium, neptunium, and plutonium. They tend to be grouped together. Now, if you look at densities as they go across on the periodic table, the orange here shows you how densities are increasing as you go across, but then the blues show you the densities are starting to decrease. So there's no consistency going across as you get to heavier and heavier elements. The elements get denser, and then they get less dense. Then denser again, then less dense. Then it jumps up denser. These are gases, so we really don't talk about density there. Then again, they're increasing in density. Then when we get to copper and go over to zinc, the density drops down. Then it starts dropping down and continually dropping down as we go across. And then they start increasing again till we get to rhodium. And then at palladium, the densities start decreasing and continue to decrease. So the periodic table is not based on densities, has nothing to do with densities. It just has to do with the number of protons that you have inside the atom in the nucleus, and the weights or the masses increase monotonically as you build up more and complex atoms. As you add protons and electrons, the masses get bigger, but they're not contained within the same volume, so that the densities do not fall in line with the amount of mass that is contained with any given particular atom. So with that behind us, let's talk a little bit about gases. Now, you've probably heard people talk about the gas law, and I'm going to talk about that. Do you have any question while I get set up here, Ranty, on that? Okay. I got to put up a piece of paper over here. My whiteboard got damaged, and I've got to replace it, and I can't write in that dark spot there, so I just tape up a piece of paper here to hide that. Okay, now, in gas laws, you probably may or may not have seen that we have pressure times volume equals N R T, where T is temperature, N is the amount of gas molecules expressed in moles, and R is the gas constant. Now I'll get into what this terminology is, but the interesting thing about gases, and this really blew me away in high school when I first heard this, and it still is quite amazing, that at a given temperature and pressure, it doesn't matter the size of the gas molecules or what the gas is, it always occupies the same volume. That is, for the same number of gas molecules of hydrogen, which is a very, very tiny atom, a very tiny molecule, hydrogen gas is two atoms bound together. We designated H2. And for a given number of these hydrogen gas molecules, and if you looked at, say, water vapor, which is H2O, which is a much larger molecule because it has oxygen attached to it. Oxygen has element number 8, hydrogen is 1. So oxygen is a much larger atom than hydrogen. But for a given temperature and a given number of atoms, they both will occupy the same volume. It doesn't matter what the size of the gas molecules are. They will always occupy the same volume for a given temperature and pressure. It's a very amazing thing. Why that is, I'm not exactly sure, but that's the way nature works. Now, N, capital N, is equal to the number of actual gas molecules, if you counted them individually and you divided by what we call Avogadro's constant, Na. Na is a very large number. It's 6.02 times 10 to the 23rd number of units or entities. A mole is a number, like dozen or a gross. A dozen of things we know to be 12. A gross of something is 144. A mole of something is this many objects. It's used in chemistry a lot. That's where it was first developed. Mole is short for molecule numbers. And 1 mole is defined to be this number, which is called Avogadro's number. So 1 mole of anything, if you had a mole of baseballs, it would be this number, 6.02 times 10 to the 23rd number of baseballs. That is a mole of baseballs. It's just a number, just like 1,000 is or a dozen is. It's just a name to express a specific number of objects. So that's what a mole is. Now, so if you take the number of objects that you have, or the number of gas molecules, small n, and divide by Avogadro's number, you have the number of moles. That's like saying if you had 36 of something, you have 3 dozen. 36 divided by 12 tells you how many dozen you have. Same thing here. If you had a certain number of gas molecules and you divide by Avogadro's number, that tells you how many moles of that particular gas that you have. Now, R is called the gas constant. R is equal to what's called Boltzmann's constant. I'll call it Kb times Avogadro's number. Now, we could also express this in this fashion at a more fundamental level. Pressure times volume is equal to Boltzmann's constant times small n times T. Same thing as this, where R is just Kb times Na, and cap N is this. So if we take N times cap R, N is small n over Na, and cap R is Kb. Na, the Avogadro numbers cancel, and it's just small n times Kb. So if you use this, the N is the actual number of gas molecules that you have in any given volume. This is called the gas law. Now, some people refer to it as the ideal gas law. This holds to a high degree of accuracy until you get to temperatures where the gas starts liquefying. Then things change, and you have to modify the gas law. And also, if you want to take into consideration the actual volume that a particular atom occupies, you have to introduce 2 parameters into the gas law. And this is called the van der Waals state equation, where we introduce these 2 factors here, an A and a B, but these tend to be very, very small, except in extreme cases, and we can pretty much neglect them and then we just have pressure times volume equals nRT. But when you want to be extremely precise and you're dealing in extreme situations, you have to account for these van der Waals forces and put in these little correction factors in there. But for what you do in your everyday life, that really doesn't matter. And the ideal gas law holds to an extremely high degree of accuracy. Now, in metric units, the pressure is expressed in pascals. The volume is in cubic meters. N is number of moles of the gas. R is the gas constant. And T is the temperature, its absolute temperature in Kelvin, not in degrees centigrade. Degrees centigrade gives you 0 at the freezing point of water, whereas temperature in Kelvin starts at what we call absolute 0, and I'll get to that in a second. So in this case, where we're expressing by the number of gas molecules in terms of moles, then R has the value of 8.31446 times and the units on this would be joules per degree Kelvin times number of moles. That's not so important to know, as long as you know that N has to be expressed in moles and T has to be in absolute temperature in Kelvin. Now, this comes about from some earlier discoveries that led up to this, called Charles's law and Boyle's law. They were experimentalists, and Boyle's law tells us that pressure times volume is equal to a constant. This is called Boyle's law. And if you look at the gas law, it tells us what is that constant. Well, the constant is nRT. If you hold temperature constant, then pressure times volume is equal to a constant. So if you're holding the temperature of a gas constant, you increase the pressure, the volume has to go down. Or if you decrease the pressure, the volume has to go up. That's Boyle's law. Then there's Charles's law, which tells us that volume divided by temperature is equal to a constant. If you hold the pressure constant. In this case, in Boyle's law, we're holding temperature constant, and in Charles's law, we're holding the volume constant. So, or not the volume, but the pressure constant. So if you hold the pressure constant and you increase the temperature, then the volume has to increase in order for this to come to a constant. If temperature goes up, volume has to go up to maintain the same ratio at a constant. Or if temperature goes down, the volume has to go down to maintain this constant ratio. That's what Charles's law tells us. Well, all that is contained in the gas law. Let's examine that. Let's look at Boyle's law. If we hold the temperature constant, we know N is constant. This is for the same amount of gas, same number of gas molecules. R is a constant, N is a constant. We're holding T constant. So pressure times volume has to equal a constant. That's Boyle's law. How about if we hold the pressure constant and we allow volume and temperature to change? Well, again, the number of gas molecules in the gas constant is a constant. And if we're holding pressure constant, then volume is proportional to temperature. See, if I rewrote this, we could rewrite this as volume equals a constant times temperature. So volume is proportional to temperature with these held constant. So it's all contained within the gas law. Now, let's look at how do we apply this into the real world. Now, the gas law tells us, I'll write it here. Is this still on screen, Renty? My hand? Okay. So I'll write pressure times volume equals nRT. This is the gas law. Now, N is the number of moles, how many number of Avogadro's number of molecules we have. Now, suppose we have a container. And within this container, we close it. We have a certain number of gas molecules trapped in there. That is our cap N. This doesn't change. As long as the container is closed up where gas can't leak out or gas can't come in, the number of gas molecules remains unchanged. That's N. Now, R is a constant. So what's going to happen if we, say, increase the temperature? So we have pressure times volume equals nR. These are constant. N is fixed. R is fixed. So we're going to increase the temperature. Well, if we increase the temperature, this product has to increase. Now, how it increases is up for grabs unless we fix one of these. If we fix the volume, like we have a container, a fixed size container with the number of gas molecules in it, V is fixed. This is fixed, this is fixed. So if we increase the temperature, it tells us the pressure has to increase. And if we decrease the temperature, the pressure has to decrease. And for that to happen, we have to have the same number of gas molecules and we have to have it within a fixed volume. Now, how about, I've got this N, number of gas molecules in here, but how about if I go and start to squish the container? Suppose this is a tight fit on the walls and we have a plunger and we start moving this down. So now we've decreased the volume of that container. Here's our new volume in here, and it's smaller than what we started with. Well, holding the temperature constant, what does that tell us? That the product, the pressure times volume, has to equal a constant. We're holding the temperature constant in this case. Well, if we're decreasing the volume, for that product to remain constant, if the volume goes down, the pressure has to go up. So, as we start squishing this gas and decreasing the volume, the pressure has to increase. That's what the gas law tells us. Or if we go in the other direction and pull the plunger out to increase the volume, so if the volume is increasing, then the pressure has to go down. As we keep the same number of gas molecules and we increase the volume, for that product, pressure times volume to equal a constant, again, we're holding a constant temperature, the pressure has to go down. Now, let's look at how about like when you're pumping up a tire on your car. Here we have, say, your tire, and you have a valve. What's happening here? Now, let's say we've started pumping this up to where the tire now has expanded to the point where it's inflated. Now, if we are to plot this thing out, let's look what happens. What's happening when we pump a tire up? We are introducing N. We're increasing the number of gas molecules going into the tire. So we're increasing N. The temperature is remaining essentially fixed during this process. It might increase very, very slightly, maybe less than 1/10 of a degree. I can demonstrate that. I can't on this one, but if we're interested later on, I can set up a very sensitive temperature gauge, an electronic temperature gauge within a tire, and show you that as you pump it up, the temperature hardly changes at all from the ambient. But anyway, we're introducing more gas into the tire. So initially, we start off with the tire, say, flat. Now, as we introduce in gas, what's happening as this tire is inflating, the inside pressure has to equal the outside pressure. I'll get into that here in a bit. So as we're increasing N, and if we were to look at the pressure, until the tire gets up to where the rubber or the tire container starts stretching, where it resists the introduction of the gas molecules that's increasing the pressure, until it reaches that point, the pressure in here is going to remain fairly constant at ambient, say call it an atmosphere. So it's going to remain essentially constant until we get to the point where it's fully inflated, and then the pressure is going to start going up. And the reason for that is if we look at the gas law. We start introducing N. We're increasing N. T is remaining constant. So R times T is constant. N is increasing. So that tells us the product of pressure times volume has to increase. Well, if the pressure is essentially remaining constant until the tire expands, then the volume has to increase. So what happens? You see the tire starting to grow until it reaches its max size. As you increase N, the volume has to increase. And then once it reaches its inflatable size, the volume is now remaining essentially fixed. And as we increase N, since the temperature is constant, the gas constant doesn't change, and the volume is no longer changing. So as we increase N, the pressure has to increase. That's what the gas law tells us. So what's happening during this stage, it'll be pretty much a linear increase. The tire might increase just a little bit once it's inflated. Of course, as you add more and more pressure, the rubber will expand a little bit, but the volume essentially remains constant, and you'll have this effect taking place. Now, let's talk a little bit about temperature. The temperature in the gas equation has to be absolute temperature, not degrees Celsius or degrees Fahrenheit. Now, an interesting thing happens is if you were to, say, take a container and let's say you have a container of a fixed volume. The volume is fixed, and the number of gas molecules is fixed. And what we're going to do is either heat up or cool down this container and measure the pressure and graph it. So we have temperature on this scale, we have pressure on this scale. And let's say we start out at room temperature. Well, room temperature is 200, well, it's very close to 300 Kelvin, okay? We don't call it degrees Kelvin, you call it Kelvin. Whereas we have degrees centigrade, degree Fahrenheit, you have 300 Kelvin, not degrees Kelvin. Now, this is at room temperature. Now, what's this telling us? Now, if you were to take this container and say we have a pressure gauge on it, and we change the temperature. So say at room temperature here at 300 Kelvin, or which would be, say, around 20 degrees centigrade, we say measure the pressure of this. Now, if we increase, remember the volume, it remains fixed, and if we increase the temperature, what happens? Well, the pressure is going to increase. The pressure gauge is going to increase a larger pressure because the volume is fixed, the number of gas molecules are fixed. So somewhere along here, we come along at a higher temperature and we measure a higher pressure and we plot it on the graph. Now let's cool it down. We take it down to a lower temperature, and we find that the pressure decreases with temperature because the volume is fixed, the number of gas molecules is fixed. So we record another data point. And you can do this at many different temperatures, and what you will find is that all these points lie on a straight line, and if you extrapolate it down to where there's zero pressure, this comes out to minus 273.15 degrees centigrade. That is what we call absolute zero. That's how they figured it out to begin with, is by plotting pressure versus temperature for a fixed volume and a fixed number of gas molecules. If you plotted pressure versus temperature, you could extrapolate down the line to where the pressure is zero, and it ends up at that temperature. And we call that absolute zero. And that has been confirmed many other ways. We can never really get to absolute zero. We can get within micro degrees of absolute zero, but we can never really get there. What happens is the kinetic energy at this point stops for the gas molecules. However, for solid materials, you can still have lattice vibrations. Not all motion ceases at absolute zero, like some people have claimed. You can still have lattice vibrations of the various atoms in a lattice in the solid, but you can't have individual atoms moving off with some velocity, some kinetic energy. The kinetic energy for free motion stops at this point, but lattice vibrations do not. So anyway, that's how we get absolute zero using the gas law. Now, in this equation here, if you're going to try to use this equation, remember, temperature has to be expressed in Kelvin, not centigrade and not Fahrenheit. So the relationship then, from this, we see that Kelvin is equal to degrees centigrade plus 273.15. Or if you take your temperature in degrees centigrade, subtract off 273.15, then that gives you the temperature in Kelvin. So that's why, for example, if you have a container and you're going to cool it down, I've seen where people have shown some videos recently of some balloons that were dipped in liquid nitrogen, and they decreased in volume. But some people expressed surprise that it didn't decrease in volume as much as they thought it should. That's because the T in here is in Kelvin, not degrees centigrade. If you go, say, from 20 degrees centigrade to 10 degrees centigrade, you are not having the temperature in the absolute sense. T in Kelvin is what we call absolute temperature. You have to measure it on an absolute scale. So, for example, say we have a balloon. We have a certain amount of gas molecules in that balloon, and we have it at, say, room temperature. T is 300 Kelvin at this point. In terms of centigrade, if we subtract off 273, that comes out to 27 degrees centigrade. So that's essentially room temperature. 300 Kelvin is a good number to know for room temperature. So we start off at 300 K, let's say. Now, we put this thing in liquid nitrogen. Well, what's the temperature of liquid nitrogen? Well, T of liquid nitrogen is 90 Kelvin. So we're going from 300 Kelvin to 90 Kelvin. So what's that tell us here? If we look at this equation, we have the same number of gas molecules, same number of moles. This part is constant. Now, the pressure is going to remain constant because what happens when you cool this thing down? You have an outside atmospheric temperature pushing on all sides of the balloon, trying to collapse it. And inside the balloon, you have a pressure pushing outward to keep the balloon inflated. Now, if the balloon remains fixed, it's not changing size, and that means the internal pressure has to equal the external pressure. They've balanced out. They've equalized one another. Well, when you cool this thing down, what happens? Well, the gas molecules start reducing in volume. So the volume now is tending to decrease, say to here. But what's happening, why is it decreasing? Because this is constant. We've lowered the temperature. So this product has to decrease, the pressure times volume. Well, if the pressure is decreasing because we have cooled the gas down, the volume is going to have to also decrease to remain keep this thing constant. They both have to, let's see here. We've got pressure times volume equals, say, some constant times temperature. Our constant is nR. Well, if we're decreasing the temperature here, then this side, this product, has to also decrease. Well, it's going to decrease in a manner such that the internal pressure of the balloon is going to equalize to the outside atmospheric pressure. So this pressure will be 1 atmosphere, the outside pressure. So this is still going to remain the same as it did initially before we dipped it in liquid nitrogen. So the volume has to go down because to equalize the pressure. So the volume is going to decrease. Well, how much is it going to decrease going from 300 Kelvin to 90 Kelvin? Well, pressure volume equals nRT. Well, T is going from 300 to 90. So that is decreasing almost 3 to 1. So this thing will decrease in size to about 1/3 the volume when you dip the balloon in liquid nitrogen. That is, the volume is decreasing. Well, how much does it appear size-wise to decrease? Well, remember, volume is the radius proportional to the radius cubed. So if how much will the ratio of the radius change? Well, it's going to change by the cube root of 1/3. So the square root of 1/3 is 1.7. The cube root of 1/3 is going to be somewhere about 1.5 to 1.6. So what's going to happen is you take this balloon, dip it in liquid nitrogen, its apparent size in terms of diameter is only going to go down by about about 60 some percent. Say at 1.5, so the volume is going to go down by 1/3, and that means that the diameter is going to go down by about 1.5, or a factor of 3/2. The reciprocal of that is 2/3, or it's going to decrease about 66 to about 66% of what it started with. So it's not going to be a huge dramatic volume decrease when you take this balloon and dump it into liquid nitrogen, because we're dealing on an absolute temperature scale, not like Celsius or Fahrenheit. Going from 300 Kelvin to 90 Kelvin is just a temperature ratio change of 1/3. So that's why that doesn't happen. Now, I can stop at this point if you have some questions, Ranty. I have some demonstrations I can do to kind of help people see what I just discussed.
Mike, right, there we go. So I know that when we were talking before, you said that you were happy to take chats from, questions from the chat, but you also wouldn't mind having a bit of a debate with someone. Is that still a possibility?
Well, yeah, that's fine. Let me get through the demonstrations first, okay?
Sure. Okay.
I need to go and check on something. I have some water boiling on the stove. I'll be right back.
No problem. Well, you heard it there, guys. So when he comes back, he's going to do a little more on these presentations, and then what we're going to do is we're going to get somebody in to have a little chat with George and see whether or not he can handle the questions from Well, there's a choice. We have right the hand and the mind of God. I'm actually leaning towards the mind of God for one reason, and that's because right the hand has already been on a few times, and I know he's going to be doing a presentation very soon, specifically on pressure as well. So I might give the mind of God this opportunity, if that's all right with everybody else and you, George.
Pardon, Randy? Say what?
We have a couple of people that would be willing to step in to have a chat with you. The mind of God and right the hand.
Well, can you let me get through the demonstrations first?
Sure, yeah, fire
It
away.
won't take very long. What I have here, I was going to take a metal can, but all I had were some metal gas cans, and I don't want to destroy my gas cans. What this is a 1 gallon milk jug. Is that coming through okay? It kind of blends in with the whiteboard.
Yeah, we see it.
You see it okay? I could put something black up on the whiteboard too.
We see it, George.
Okay. Now what I'm going to do is I'm going to take and I'm going to pour some boiling water. I just boiled some water on the stove. And I'm going to pour it in here. Shoot. Now, what I'm going to do is mix it up good. What we're trying to do is create some water vapor inside, and I'm going to seal this thing off. And we'll let it cool down in time, and I'll just have it hanging here while I talk, and we'll see what happens, and then we'll try to explain using the gas law as to what happened. So is you're seeing this okay hanging here? Okay, so we'll just let that stay there and cool down. It's very hot right now. So what we're going to have, let's see, I'll move this over here. Is this still in camera range? Okay. Now, using the gas law, what we have is this container here, this milk jug. Okay, we're starting off, it's open. So the air inside is at the same atmospheric pressure as outside. So the walls don't move. That the net force is 0. You have force pushing outward on the container, and you have air pressure pushing inward on the container, and they balance out as long as it's open. So the container remains intact. Now what I did is I introduced some water. I put some boiling water in here, and what I did is I shook it up. Well, why did I shake it up? Well, I'm trying to heat the air gas molecules up. I'm trying to heat it up so that the gas molecules have a lot of kinetic energy and escape out. And we also have in this area a lot of water vapor replacing the air molecules. And then we cap this thing off. Okay? Now, what we have inside is a mixture of hot air and water vapor. Now, as this thing cools down, what happens is we start creating a vacuum inside here because the gas molecules are slowing down, they're cooling down, but more importantly, the air that we replaced with water vapor is condensing. It's no longer a vapor, it's no longer a gas, it's condensing, and it's falling down to the bottom of the container and has an extremely small volume compared to the water vapor. Water vapor takes up a lot more volume than liquid water, and that's what's happening. As this cools down, the vapor is condensing and forming water, and we're getting a vacuum in here, or a much lower pressure. The pressure inside now is decreasing. Well, given the gas law, I've capped it off, so I fixed N. I fixed the number of gas molecules inside the jug. And the temperature is going to decrease. This is a constant. So what does that tell us? Well, the pressure times the volume has to also decrease as the temperature decreases. So this product has to decrease. Well, it will decrease to a point where the volume decreases to a point where it builds up the pressure and the collapse of the jug stops. The collapse of the jug will stop when the internal pressure equals the atmospheric pressure outside. Then it will stop collapsing. Well, during that case, the volume is decreasing. Now, you should be able to see, can you see how the thing has been crushed? Is that coming through okay, Ranty? Can you see that we no longer have a nice container? It's still pretty hot. This will keep decreasing as the temperature decreases. I could speed it up here. I'll put a little cold water in my okay, because I could cool it down by putting it in cold water. But that is the reason. That's what's happening, is the water vapor inside is condensing. It's lowering the internal pressure, so the volume has to decrease in lockstep to increase the internal pressure to equalize and become equal to the outside pressure. Now, one other thing I'm going to show you here is I made this apparatus. This is from one of those party balloons. It's a Mylar helium balloon with no helium in anymore. And I have it totally collapsed. And I was trying to think of a way of making a sensitive pressure indicator. And it occurred to me I could use it, do it with one of these party favors, you know, that you blow into. And it expands. Well, it doesn't take much pressure to make that thing go out. You hardly have to blow at all. So that's a very nice indicator to tell you if the pressure has increased or not. So what I'm going to do here is show you with this balloon exactly what I talked about with the tire here earlier. I'll just get rid of this. Let's just hang this over here. Okay, now I have this deflated balloon. So the balloon is sitting here, it's deflated, and I have a straw sticking in here, and then I have a takeoff on that straw for my pressure indicator. And what I'm going to do is I'm going to introduce gas molecules. So we have PV equals nRT. So I'm going to increase M, the number of gas molecules that are flowing into the balloon. So N is going to be going into the balloon and expanding it. And then here I have my pressure indicator to see what the pressure is going to be. Well, the claim is until the balloon expands and reaches its maximum size to where the skin of the balloon starts resisting any more introduction of gas molecules, that the pressure is going to be essentially the same as ambient temperature. The pressure is not going to increase until this thing inflates. So what's going to happen is as I add gas molecules, the pressure is going to remain constant at atmospheric pressure. And then once we reach the fully inflatable size of the balloon, the pressure will start increasing. So let's take a look at this. Now I'm going to blow and start inflating this, and watch this. Again, this is my pressure indicator. Doesn't take much pressure to make the thing go out. So I'm just going to start inflating this balloon. Now watch what happens once it inflates. See, pressure is increased at that point. So that shows you that until the balloon or your tire is fully inflated, the pressure inside is going to remain the same as the outside ambient pressure. So if you want some people to come in and start discussing, that's fine.
Okie dokie. Let's see. The mind of God. I'm going to try and get a hold of the mind of God and bring him through. So let's get my cell phone. Let's go and find. Where are we? Let's increase that. There we go. Okay, so what I'm going to do is I'm going to invite the mind of God to join this call. 1 second.
I'll be right back in 30 seconds. I'm going to take some stuff back to the kitchen.
Okay. Okay, so I'm adding you to the call there, and the mind of God, let me know where.
Okay, I'm here.
Okay. There we go, I think we're all on. Let's bring you guys back on. Right, George, do you want to meet Chirag? Chirag, do you want to meet George?
Hey, what's up? Can you hear me?
We can, yeah.
Yeah, no, George and I know each other.
Okay, cool.
What's up?
Hey, George, can you hear?
What's the question? Hello?
Right, you two guys carry on.
George, what's up, man?
Well, just working on the gas law.
Okay, so was that just more general edification, or was there a flat earth reason behind that? Ball earth reason?
No flat earth reason whatsoever.
Oh, okay.
Just to generally educate people as to how gases work and the gas law. I mean, we can get into the Earth's atmosphere and that sort of thing following from this, but that's just basic fundamental principles.
How do we understand that the notion of the mass attracting mass in this PV equals nRT framework, where this gradient that you guys talk about being a function of gravity?
What gradient are you talking about? The atmospheric gradient?
Yeah, that's a function of gravity, right?
Well, gravity causes that, yes.
Right. So is there a way to link it to this, or is it acting independently?
Well, you have to be careful in how you use the gas law. Here, I'll show you. We have PV equals nRT. And let's say we have the Earth and we have the atmosphere surrounding the Earth.
Mm-hmm.
Now, you can think of when we're dealing with the gas law, we have a volume. Volume implies some sort of a container holding the gases. Well, what's a container in the atmosphere that surrounds the Earth? Well, the container is a force field container, much like if you look at the Princeton Tomahawk fusion project, where they're holding plasmas at extremely high temperature to initiate a fusion process. Well, there's no material on Earth that can contain a fusion reaction without the container being melted or destroyed. So what do? They create what's called a magnetic bottle using magnetic fields in which to suspend the plasma so that you can initiate a fusion reaction. Well, you could say the same sort of thing is happening here. You have a force field, which we call the gravitational force. We have an accelerated field that the Earth being so massive, the Earth has a mass on the order of 10 to the 24th kilograms, extremely large mass. The mass of the sun is on the order of 10 to the 30th, kilograms, 10 to the 30th kilograms, about 1,000,000 times more massive than the Earth. But nonetheless, given Newton's force equation, force is equal to G times the product of two masses, let's say the mass of the Earth times the mass of the gas over the separation distance squared, is if we take where this is the radius of the Earth essentially to the atmosphere, this is the radius of the Earth. If we take this is essentially a constant, and if you put in values for big G, the mass of the Earth and the radius of the Earth squared, you get the value F equals little g times some mass, and we call this the weight. And this little g is 9.806 meters per second squared. That is what this calculates. Big G times the mass of the Earth divided by the radius of the Earth squared comes out to that value. So this is force equals mass times acceleration, the first law, or second law, Newton's second law of motion. So essentially, you have a container. It's a force field container that keeps the atmosphere, the gas surrounding the Earth, in place about the Earth. All the gas molecules are attracted towards the Earth and remain in place in a spherical shell about the Earth. It's a force field that holds it there, much like in a tomahawk magnetic field bottle is containing a plasma to have a fusion reaction. So,
but wait, George,
it's not a physical barrier. It
George.
is a barrier in a sense that the container is this force field.
Okay. One question, man. So the P in PV equals nRT, you're saying that is a byproduct or allowed to happen because of what you just went through, right? This force field, the pressure in PV equals nRT?
Not entirely. I mean, this is independent. This could be on the surface of the Earth and has nothing to do with the gravitational forces of attraction. In this case, for the Earth's atmosphere.
Yeah, that's what we want to know about. We understand on a local level. I don't think anyone would argue if you have, a tire.
Well, what you'd have to do is this holds for any given volume, small volume within the atmosphere. You pick out some volume, say, at the surface of the Earth or up at Mount Everest or out at the Kármán line. This equation holds for that local volume or that slice of volume within the Earth's atmosphere. Now, if you're trying to describe the whole atmosphere, this equation doesn't exactly give you the whole picture because this volume is so huge that it allows pressure gradients to form. There's no pressure gradient information in that equation. That is assuming that the volumes are small enough so that you don't have gradients occurring.
Yeah,
agreed. The weight of the gas above the gas on the bottom of the container is essentially, the pressures are essentially equalized throughout the volume. That's what this thing is assuming.
It's not just a gradient thing, it's a homogeneous thing too, right? It's assuming one type of, gas, right?
No, that's what I stated to begin with. That's the amazing thing about gases. You can mix all kinds of gases, and this equation holds. It doesn't have to be homogeneous. It doesn't have to be one particular type of gas. There is a law called Dalton's law, which is also amazing. Dalton's law states that the partial pressure of any collection of gases is equal to the sum of the partial pressures of the individual gases. So you could take the partial pressure of water vapor, the partial pressure of nitrogen, the partial pressure of oxygen, mix them all together, then the net partial pressure of that collection of gases is just equal to the sum of the partial pressures of the individual gases. It's an amazing thing.
No, we're cool with that. We're cool with that. Sorry, I appreciate that. So I guess for all of us as flat earthers, and I'm not trying to be rude, but like I think we're trying to get an understanding of this force, quote, force field and how it relates to PV equals nRT, and you're saying it not directly tied to the P, but it's allowing pressure to exist, right? Fundamentally, wherever you take a sample.
This PV equals nRT, you have to have a very well-defined volume in which there aren't gradients, in which there are not pressure gradients.
We're cool with that. Yep, that's fine. Fair enough. So you can take small samples anywhere in our quote universe or space or whatever, and that will hold, right?
Yes.
Small enough. Yeah. Okay. So then now the what is creating this pressure, you would say it's this gravitational quote field or thing that you just described with your yellow and that thing, right? You're saying that gravity is allowing that P to exist.
Well, let me get to that here. Say we have the surface of the Earth here, okay? This is just an expanded view of what we have. I'm taking a very small slice.
Why
say there.
Curved?
Okay?
Okay, go for it. It's flat.
Can you see that okay? Oh, yeah, it's there. Now, what is happening is if we have gas in the atmosphere, we end up with a layering. We have gas molecules hugging the surface of the Earth. Let me express it this way. Let's say it's fairly dense. You know, it gives us a pressure of 14.7 pounds per square inch, or 101.325 kilopascals. And then as we move above the Earth, this starts thinning out and getting thinner and thinner, less dense. There's less air as we move higher and higher to the point where the density of the atmosphere or the air in here essentially reaches a near perfect vacuum. It just gradually merges. So if we were to make a plot of height above the surface of the Earth, this is height, and the pressure, then we will find that we have one atmosphere at the surface of the Earth. Here we're at the surface at 14.7 psi, and the pressure kind of goes linearly, and then, it's wrong. I got to go the other way. We start out here at 1 atmosphere, and as we go up in height, the pressure starts decreasing linearly, and then it kind of goes exponentially towards 0, and then kind of asymptotically approaches 0. So the pressure, it's not a linear function with height, because if you take a column of air.
But George, the claim in the Helio model is it never goes to 0, right? It always approaches 0?
Right, yeah. There's no such thing as a perfect vacuum.
No, I'm just asking.
Deep space, there's a few molecules of something out there per cubic meter. It's never a complete void of nothingness. I mean, for all practical purposes, yeah, it's as good to close to a near perfect vacuum as you're going to realize. I mean, if you have, say, a handful of molecules of something per cubic meter, that's pretty rarefied. That there isn't that much there. But nowhere in deep space do you get exactly down to 0.
Have you?
Yeah. Okay. Yeah, that's fine, Ranty. I think it's, for me, I think a lot of us are still kind of struggling, or maybe flat earthers would need to understand, how does PV equals nRT fit into the framework of like ball Earth? But It looks like P is able to be generated by this gravitational field. So that's what it is for them.
Is that your conclusion there, George?
Conclusion of what?
How this P can be generated in without an actual physical quote V.
Well, I'm showing you that here. Here's the surface of the Earth. Now we have denser air, and the air gets more rarefied as we move up. So, what determines the pressure that we feel at any given height above the surface of the Earth? Well, that's determined by the weight of the air above us. Air has weight. Every molecule has weight. So, just like you have a bushel basket full of, say, marbles, if you fill that thing full of marbles, there's a lot of weight that you have to hold up. Now, if you empty that so you have half as many marbles, then there isn't as much weight. Every molecule is like a marble. Everyone has a certain amount of weight. Well, the total weight that is above you is determined by the collection, the total number of gas molecules pushing down on you. Well, the higher you go up, the fewer molecules you have pushing down on you, so there's less weight. And if there's less weight, there's less pressure. Remember, pressure is force per unit area. So if you have a certain amount of weight, in this case of the total number of gas molecules that push down on any given area, if the area is held constant, then the higher you go, the less weight there is above you, so the less pressure there's going to be, because the force is nothing more than the weight of the gas molecules, and this decreases as you go up in height. Area remains the same. Your cross-sectional area that you want to look at the pressure over, or the force over, these gas molecules are pushing down. So as we go higher and higher, there's fewer gas molecules to contribute to the weight, so there's less pressure. And by the time you get down to the surface, there's all this gas up above you, 20 miles worth of gas pushing down on you. So the pressure is going to increase because the weight of all this gas up above you is so much larger than it would be, say, if you're up at the top of Mount Everest. You have fewer gas molecules above you pushing down on you. That's why there's higher pressure down at the surface of the Earth than there is anywhere at any given height. As you go higher and higher, the total collection of the weight of the gas pushing down on you has to decrease because there's less gas molecules.
No, okay. I don't know, Ranty, if you needed to go into something else or...
Yeah, I mean, I can ask a few questions if you like from the chat.
Yep.
Is that all right with you? Yeah?
Yep. Thanks, George.
Okay.
Okie dokie, right. So we have from LBB Store, please explain how our tiny sun can remain in hydrostatic equilibrium with a vast expanding universe.
What? Repeat that again?
Please explain how our tiny sun can remain in hydrostatic equilibrium with a vast expanding universe.
Oh, well, that doesn't have anything to do with the subject at hand, but, okay. With the sun, there's a couple mechanisms occurring. You have a sun in which is a nuclear furnace. You have hydrogen gas molecules that make up the sun and helium. Well, what happens is a thermonuclear process where hydrogen is fused together to form helium, and in doing so, it gives off tremendous amounts of energy. Well, you have so much mass in the sun. Like I said, the mass of the sun is on the order of 10 to the 30th kilograms. You have this gaseous ball. It doesn't matter whether a gas is or a mass is a solid or a gas or a liquid. There's still mass there, and it has the same attractive properties. Gases, liquids, and solids all have the same attractive properties, from force equals gravitational constant times the product of the masses and the distance between the two masses squared. That holds for any type of matter. It doesn't matter, doesn't necessarily depend on the state of the matter, whether it be, solid, liquid, or gas. So in the sun, you have all this helium or hydrogen, and it's all attracting one another. So you have this compressive force going on inside the sun that's tending to collapse the sun into a very, very dense sphere. And in doing so, as it collapses, it generates an extreme amount of heat because the pressure is getting so great. Remember, the density is increasing. We have a certain amount of mass. Remember, density is mass per unit volume. So if for a given amount of mass, as the volume decreases, the density is getting very, very large, and that creates stresses and increases the pressure tremendously to the point where it really heats up. Well, it gets heated up to the point where fusion reactions can occur. That two hydrogens are fused together to create a helium atom. And in the process, that gives off a lot of energy, this thermonuclear energy. So what you have then on the inside of the sun is you have this thermal temperature that's tending to expand this stuff outward. And so it reaches a balance. There's an equilibrium between the thermal expansion of the gases in the sun going outward versus the compressive nature of the gravitational field trying to compress it, and it reaches a point where there's an equilibrium, that there's just same amount of thermal pressure trying to expand these gases outward to blow the sun out into space versus the gravitational forces of attraction that are holding it together.
Okay, we have a lot of questions, so if we can I'm just going to copy this last one from Brian, and then we're going to crack on. So we have next question from Oxbow Spirit. Why did George use containers in his demonstration and not use gravity?
Because I can't generate enough gravitational mass to do any sort of demonstration. You got to remember that the Earth is extremely massive. It's on the order of 10 to the 26 kilograms. How much mass can I put together in a reasonable amount in my living room or in my yard is, let's just work out some numbers here. The density...
Well, no, I mean, you don't have to go into the details of
okay. I can't. Okay, I can't. Short version is I can't assemble enough mass to create a gravitational field that will mask out the Earth's gravitational field so that I could do a demonstration. Okay. Now, the only way I could reasonably do it with any sort of real world amounts of mass is I'd have to go out into deep space away from any planet where I'm not influenced by the gravitational fields of, say, the Earth and the Sun and that, so that I could conduct that experiment. In principle, I could do it in deep space, out away from any sort of massive objects like planets and stars.
Okay, so another question. Does the natural laws pertaining to gas pressure apply to the astronaut suits?
Yes, of course.
Okay, so moving on from that, is the thickness of the astronaut suits affected by pressure and temperature? What would be the results of drastic temperature changes and equal pressure in suits?
Okay, well, let's take, say we've got this, I'll just represent an astronaut by this rectangular, here, I've got a rectangular astronaut, and we're putting a pressure suit around him. And what we do is keep in mind that, say, out on the moon or in space, the pressure out here is essentially zero, okay? For all practical purposes that we're talking about, that the pressure out here is zero. Now, the human body here on Earth, we're used to having a pressure of 14 psi, 14.7 psi. So what we have to do in the ideal situation is we'd like to have the internal pressure here being 14.7 psi surrounding the astronaut. But in order to do so, remember that the total amount of force is pressure times area. So if this suit that surrounds a person is a lot of area, and the amount of force is going to be tremendous. So what you do is you figure out how much pressure you can reduce around a person and keep them comfortable. For example, on an airline flight where you're up at 30,000 feet, they reduce the cabin pressure inside a jet down to the same pressure as where you're at about 7,000 feet. That's kind of the federal regulations for doing that. And that pressure, like in the cabin pressure of a jet, is put at about 11 psi. And you're comfortable at that pressure. You could probably reduce it even more for the astronauts, but let's just say for purposes of illustration, let's say you could keep the inside pressure of the suit at 10 psi, about 5 psi lower than what's on the surface of the Earth. And if you look at the construction of these spacesuits, they're rather intricate. They're interwoven materials, so it doesn't blow out. It's essentially a balloon with a very tough, thick, or a very tough skin. It's not necessarily very thick, but it's very tough. It's got interwoven threads in that to keep the bag from blowing out. A very good video on this. I'll give a plug to Jim Panda. He has done an excellent video on spacesuits. Go to his channel and look at his video. He analyzed or researched this rather in depth and did what I consider a very excellent video. So I would go to his channel and look up his video having to deal with spacesuits and what they went through in the development of the spacesuits and what they ended up with. So this is not an impossible problem to solve. It has been solved, and it is not an issue. You're not going to have, these spacesuits aren't going to blow out when you inflate them, say, pressurize the internal to 10 or 11 psi, or probably even 14 psi. Knowing the way NASA and the government does things, is they make sure that there's plenty of margin in these things, and they're probably rated to even beyond 14.7 psi to ensure that the spacesuit will remain with its integrity and not blow out.
Okay, I've got a bunch more questions, but I'm just going to read out a few of these super chats before I get behind, because there's that many coming through right now. So we've got George equals globe zombie regurgitating pseudoscience. Next one. Okay, so where is the curvison, dear globe zombies? Word of the day, globe diarrhea, zombies love it. Ask the globe zombies how to test distance to Polaris. Don't swallow gravity, bullshit. She will infected you with globalitis and you'll be regurgitating pseudoscience and you'll be suffering
Randy,
spinning balls, wet dreams. Yep.
Hey, Randy, why don't you find some serious questions instead of wasting time with that nonsense?
Well, 1 second. Stay away from gravity, the bitch is nasty. So I'm going to carry on with the questions. George, can you explain this with relative density disequilibrium instead of a force field?
That sounds like an Arwin question. Disequilibrium. I hate the use of that word. That really is not a technical term used in physics or engineering. Disequilibrium is a term that's used in economics to describe the unequal balance of economic systems, and nowhere in science and engineering do we ever use that term. What we talk about is things not being in equilibrium. But if you want to call it disequilibrium, fine. Relative densities don't have a direction associated with it. It's not a vector. Density is a scalar. Density is mass per unit volume. There's no direction associated with mass or with volume. So if you're talking relative densities, you're talking differences in scalars, whereas with gravitational force fields, there's a particular direction associated with it, and that's directed towards the center of the Earth. So everything is the direction of what we call down anywhere on the surface of the Earth is pointing from the surface to the center of the Earth. So if you're up here, say if this is the North Pole, your sense of down is going down beneath your feet, which is pointed towards the center of the Earth, and someone here at the South Pole has that same concept. They're standing on the South Pole, down is going from their head to their feet, and that's directed towards the center of the Earth. So anywhere on the surface of the Earth, the sense of down is from that person towards the center of the Earth. So there is a preferred direction for the movement of objects. When we take them up above the surface of the Earth and let them go, they're going to fall down, and they will do so in a direction to follow a vector that's directed towards the center of the Earth. That's what we call down. So relative densities have no preferred direction. Who's to say that an object with some, say, density rho 1, let's say this is 10 grams per cubic centimeter. Water is 1 gram per cubic centimeter, so this is 10 times denser than water. And we put this thing in water, which is 1 gram per cubic centimeter. The reason why it moves is because of the gravitational force field pulling it through the liquid water. But if you put this thing inside a vat of water, there's no preferred direction in densities. Who's to say it wouldn't go laterally go down or go up without a gravitational field to tell it in which direction to move? There is no preferred direction with densities.
Okay. Ask if the gas law would hold true on both a flat Earth and a globe Earth.
Sure.
Cool. There's a few people that have asked that, so that was the most easiest way to get that question out. We have a question from the Adam Meakin. Can you explain this with sorry, that was the wrong one. Could George do a demonstration of gravity maintaining a force field for gas?
Again, I explained that before. I can't do that because the mass of the Earth is so much greater than any sort of mass that I could assemble to create an experiment, to do an experiment. A mountain the size of Mount Everest pales in comparison to the mass of the Earth. Even if I were to construct a mass the size of Mount Everest, it would still be overwhelmed and overpowered by the gravitational field of the Earth. There just isn't any way on the surface of the Earth to conduct any experiments to create artificial gravitational fields to do this in a reasonable manner. Now, there's one way you can do it. There is a video out there that shows where somebody had a very sensitive scale and they had it mounted, say a sensitive scale. I have a scale like this. I could maybe demonstrate that sometime. I have to figure out what went wrong with the scale, but I have an OHA scale that will measure accurately 0.01 grams. And basically what was done, the scale was mounted up on some sort of a platform, and it had a little pyramid of lead hanging from that scale. And the scale registered, I can't quite remember, I think the number was something like 132 grams or 152 grams for that pyramid. And then what they did is they took a sphere of lead and moved it underneath and found that the additional mass added to the Earth directly underneath the pyramid changed the reading. It went from, say, like 132.001 to 132.002. It changed in the thousandth digit, demonstrating that something was going on here. By adding a little more mass underneath that pyramid that they were weighing with a gram scale, increased the weight when that spherical lead ball was put underneath. Now, that's one way you could demonstrate it, but the effect is so small because you're dealing with, to get this 132 grams, you've got this 10 to the 24th kilograms of the earth underneath pulling down on it, and you're adding this mass of lead, PB, underneath there, and, you know, it's increased it like a factor of 1 out of 100,000. I mean, it's a very, very small effect.
George, we'd like to see that. George, we'd like to see that, and then take the ball away and then have the number go back. We would like to see that.
Yeah, that would be a fun thing to do.
No, that would be a major accomplishment in Ball Earth.
I said that would be a fun thing to do. I'll look at getting my scale repaired to maybe where I could do that. I don't know if my scale is sensitive enough at 100th of a gram. I think you have to get down to, I'll figure it out. I'll go through the numbers to see what kind of resolution you need on the scale. That scale that they were using in that demo was an extremely precision piece of equipment. And
but George, you would show us the whole apparatus and then the reading and then move it in and then move it out, right? You wouldn't just do
that'd be an interesting thing to do. In fact, it'd be interesting to say even double the mass underneath.
Do you genuinely believe that those objects are interacting in some way? Like you really think that something's happening between them?
Yeah, the mass underneath the pyramid is increasing, so you're getting more of an attractive force down towards the Earth.
So it has awareness of the things around it somehow? Like, so that would be almost supernatural.
No, I mean, this stuff isn't sentient or anything. They don't have any self-awareness. They're objects.
Can we also do it with different materials?
Sure.
Okay,
but
it's just the mass,
why
right?
they used lead is you have to have a fairly significant amount of mass.
I understand, yeah.
You could do, say, if you could find a tungsten sphere or spent uranium or gold. Well, gold's pretty expensive, but lead isn't anywhere near being as dense as gold or tungsten or spent uranium. The density of lead is on the order of about 11 grams per cubic centimeter, and the more denser materials that we have, like gold, tungsten, is twice that. So
what's hanging from them?
Two spheres, one of lead, or three spheres, one of lead, one of aluminum, and one of tungsten or spent aluminum or uranium. You should be able to register different numbers here as you move these different objects underneath.
What's the scale holding? What material is that pyramid that's dangling from the scale?
That was lead.
Okay, so is the size of that, is that fairly significant, or how high did you dangle this thing from? How high was that thing? This scale set up?
I think the separation distance between the surfaces was on the order of about 2 millimeters.
Yeah, I mean, if you do that...
It was a fairly narrow gap.
I would say if you do that with different materials and give us a way to, I don't know what kind of scale you're using that could do that, that's something.
Well, I'm saying it has to be, it's not a cheap piece of equipment. To get a scale to register on the order, give you a resolution on the order of 1,000th of a gram, it's no small matter. You can easily come by scales on the order of $1,000. That's what I paid for my OHA scale. That gives me a 100th of a gram resolution. I don't know what it would cost to get a scale of that caliber to register on the order of 1,000th of a gram. But I have a digital scale that will definitely read in the 100th place. And
what were those clowns using on the YouTube video? That there's a YouTube video posted where they flash to the thing and then they flash to the scale reading, and then this looked like it was done at least like 10, 15 years ago. Like, what, that scale looked like a piece of garbage, but it was showing.
Well, the looks are deceiving. I mean, you might think it looks like a Tinker toy or something. Laboratory scales that can resolve on the order of, second, third decimal places, they don't necessarily look pretty because it's a very intricate piece of equipment. And a lot of times, like in standards labs that I used to work in, sometimes you cobble this stuff together to push the state of the art. They don't necessarily look like nice, pretty machine pieces of equipment in order to push the state of the art. A lot of times you have to really jump through hoops and put things together that haven't been done before. And I know that video you're talking about. I've seen it, and that scale, though it isn't pretty like some consumer scale, nonetheless, it allowed them to register the differences in the weight on that pyramid as you moved a spherical mass underneath it. I mean, just because something doesn't look pretty doesn't mean it isn't valid.
No, I mean, fair enough. But I think something like that, to me, if that were true and understood that could be done, even with an antiquated looking scale, I mean, that's pretty compelling. It doesn't necessarily prove the geometry of the Earth, but it certainly makes a strong case for the possibility, at least, that mass can attract mass or have an interaction with one another at a distance. It's something for sure. But yeah, I mean, if the scale is really expensive, I think my last statement before I got to go, I think it's getting to the point now where people are looking for a unique solution, and I don't know if it's just me, but I think more and more people are looking for a common test or whatever it is that is unique and mathematically like rigorous. And so I'm not saying these discussions are useful.
Well, the thing is it is not my mission in life to prove things, to spend money to prove things to flat earthers. I did it once in measuring the curvature of the Earth a couple winters ago, in conjunction with some research I was doing on refraction over ice. But if you want to do something like this and do a fund me page or something to come up with the money, I'll find where we can purchase the scales, but I'm not going to put my money into it.
No, I'm not talking about this. I'm talking about, just a test. Like I'm talking, this is more academic, I think, what you were going through today, but
it's not academic. I mean, this is something you can do very easily in the real world with the right equipment. Just that you have to, sometimes the right equipment costs a lot of money.
Okay.
You're just not going to go down to your local Kmart or Walmart and buy a scale that can resolve a thousandth of a gram. These are precision pieces of equipment, laboratory grade pieces of equipment. Just like you're not going to go to your local hardware store and buy a voltmeter that can resolve 8 digits. I worked on projects like this at Hewlett-Packard where I designed very precision pieces of equipment. We designed, the last project I was on, we designed a voltmeter that could resolve a tenth of a part per million, or a hundredth of a part per million. 1 out of 10 million. That was 8-digit accuracy. You don't go down to a store and buy that. Hewlett-Packard still sells these. This meter that I helped design, it cost $10,000 to buy that particular meter.
But George,
there's a lot of technology that goes into putting these things together.
Do you at least concede how it's difficult for us as flat earthers to believe that will happen, because there are literally an infinite number of interactions like that happening, and we don't have any, at least from a very cursory level, we don't see that's quote scale changing. Do you at least?
Well, of course you can't, because it's such a small effect.
No. I'm saying everywhere around.
Sort of practical masses that you can assemble to do these things. In order, if you're using something on the order of 10 kilograms or something on this ball moving underneath the pyramid, that isn't a very big change compared to the delta increase in mass relative to the Earth. Again, the Earth is 10 to the 26 kilograms on that order. I think it's like 5.9 times 10, it's around 6 times 10 to the 24th kilogram, somewhere in there. So in the fact that you can't assemble a large mass to demonstrate the effect means you have to come up with some equipment that can measure these minute changes. Now, if you could assemble a huge mass then you can demonstrate this thing probably with a bathroom scale. But nobody is going to be able to do that on the surface of the Earth. It's just the mass would have to be so incredibly large in order to use a digital scale that you get, or a bathroom scale to do that sort of thing. So you have to resign yourself to using precision, laboratory grade instrumentation in order to measure these differences.
Can I just ask a question? If you're suggesting the only variable that you're changing is by including extra mass underneath the underneath this triangle, yeah, to measure it. But is that the only variable? I mean, is there no other forces acting on it, like magnetism or anything?
Well,
like
you
that?
can eliminate all the other variables. Let me draw it here again. Say we have a table sitting here, and we have our scale.
But yeah, Rand, just answer that. That's why we would want many materials used, not just whatever, one or two.
Let me just talk about this in a second. Let's talk about what could possibly be affecting it. Now, this triangle is it's a prism made out of lead, PB, okay, lead, and lead is somewhere around 11 grams per cubic centimeter, somewhere in that range. And you're putting this spherical mass underneath it. Doesn't have to be spherical. It could be a cube or whatever. And you're registering a difference in the weight. Well, what could possibly be else affecting it? Well, if you think it could be air currents, then just enclose it in a container where air currents and hold it at a constant temperature. You could insulate it with styrofoam to keep the temperature constant inside this thing. So you can eliminate, let's say, temperature. So the temperature is out of the question. We can easily assemble this thing so temperature will not be an issue. How about changes in air density? Well, again, if it's a closed container held at a constant temperature, then given by this, temperature is constant, the number of gas molecules in here is constant, so this side is constant. The volume is constant, so pressure has to be constant. So we can keep the pressure constant and the density of the air constant. Well, how about electrostatics? How about electrostatic attraction? Well, this is a metal. This could be a metal. This could be lead, could be gold, could be silver, could be copper sphere, could be any sort of a metal sphere, mercury, whatever. Well, these being conductors, you can easily get rid of the electrostatic forces by just grounding them. To this, you'd have a wire going to ground, and to this scale, you can also ground this to the same potential. What happens if you put these two to the same potential? Then there's no potential difference between them. The potential difference is zero. If there's no potential difference, there can't be any electric field between them. There can't be any electrostatic forces that would cause this to change if they're at the same potential. So that's very easy to do. You could put this in a metal box. You could ground the metal box. So everything's at the same potential. Can't possibly be any electric fields in here because this would be a Faraday cage. Inside a Faraday cage, the electric field is necessarily zero. Is always zero inside a Faraday cage. So you can totally eliminate the electric static field effects. How about magnetic fields? Well, same sort of thing. You could encase this thing in mu metal. So magnetic fields won't penetrate. If you have a magnetic field, this thing is, say, a ferromagnetic material like iron or a high permeability material, what we call mu metal, Mu, and you encase that with that. Then if you have a magnetic field, what would happen is if there's a magnetic field coming in, it will be diverted around. The mu metal forces the flux lines to penetrate within the mu metal, and so they do not appear inside. So the magnetic field would just be diverted around the thing. So you can eliminate magnetic fields, you can eliminate electric fields, you can eliminate temperature. So
George, so just to be clear though, because I know the demonstration you're talking about, I've seen it. It's an old video, isn't it? The video that you're talking about, they didn't have any controls like this around the actual experiment.
I don't think all they were trying to do, from what I could gather in that video, they were just trying to demonstrate the principle. It wasn't intended to be a scientific experiment where they eliminated everything. People glom onto it. I mean, that was done, probably maybe back in the 60s or the 70s before anybody thought about, trying to demonstrate this stuff to flat earthers or anybody else. It wasn't a precision experiment.
And they had a scale that could go down to the thousandth of a gram then, in the 1960s and 1970s.
Yes.
Okay. What would happen if you put a mass of lead above the dangling...
Put it over here?
Yeah, above it instead of underneath it.
Yeah, you'd expect that the mass or the weight would decrease. It wouldn't increase, it would decrease, because what you would have is you have the gravitational attraction of the Earth pulling downward. Now you put this mass here, and that's going to counter it. So it should decrease it by the same amount.
We have a question from Sky's the Limit. Question for George. What about the fields inside? Maybe it's just separating the magnetic and electric fields, making a small one inside and a big one outside.
Well, I just explained that. If you have a metal box, you have what's called a Faraday cage. There are no fields inside. That's a necessary condition of electrostatics. You can easily demonstrate this using and prove it using Gauss's law, that inside an enclosed metal container, inside a good conductor, all fields are zero. Zero. They cannot penetrate a Faraday cage.
Okay, so if the moon was passing over, would the moon affect it?
Yeah, of course.
So would you have to actually do your experiment at a time when the moon was nowhere around?
Yeah, I mean, you could do it several times throughout the month to see if you can even see. I haven't done the calculations. I don't know. In principle, yes, the moon, if the moon came up overhead, its gravitational field would pull upward and tend to lessen the weight of that. But how big of an effect? Remember, the moon is 230,000 miles away, and the mass is about 1/10 that of Earth. I'd have to go through the calculations to see at what level that would change. Now, if this happens to change, say, in the 10,000th digit, 10,000th of a gram, then it's not going to matter. I can't tell you, I haven't gone through the calculations to know at what level the moon moving in and out would change the weight of that. It just might not be significant and not register on the scale, but I don't know that. I haven't calculated it.
Okay, so a different line of questioning here. Can you ask George if he can show this force field in the Vomit Comet when it's weightless?
The force field? You mean gravitational?
Yeah, you were talking about your force field before.
Well, no, not really, because the problem you have there, I'll illustrate that, in this so-called Vomit Comet. What's going on is here you have the, say, surface of the Earth, and you have this jet, and what you're doing is you're going up in a parabolic trajectory and then coming back down. And so as you're going up at a high rate of acceleration, and then as you start reaching the peak, you're deaccelerating, and then you reach the peak, and then you start falling and accelerating. So in this time period, which tends to be about 30 seconds, I believe, you can experience what we call weightlessness. You're not eliminating the force fields of gravity. All you're doing is countering them. Is what Einstein has showed us. You can, I made a recent video about Einstein's relativity, on how he developed his relativity theories. You might watch it. It's in Einstein's own words. I read from one of his lectures. And what's going on here is, if you're in an Einstein's general relativity tells us that you cannot tell the difference between a gravitational force field and an accelerated frame of reference. So, for example, if you're falling in free fall down towards the center of the Earth, and you put a scale underneath you, that scale will read 0. An accelerated frame of reference creates a new gravitational force field that counters the force field of the Earth, so that the net gravitational acceleration is 0. You can't weigh yourself in free fall by putting a scale underneath your feet, because you are in a new frame of reference in which there's a gravitational force field due to your free fall that counters the gravitational force field of the Earth. So there isn't any way with the Vomit Comet that you're talking about, if I understand the question correctly, is that there isn't any way to actually determine from your accelerated frame of reference versus the gravitational force field, to parse them out, to separate them out. I don't know of any way to really do that. All you can register is the net effect of one countering the other.
Right, okay, so Sky's the Limit is coming back to his original question. So, George, my point was, a small field inside compared to the one outside, it would look like nothing. Even if it keeps the fields outside from going inside, that says nothing about what is already inside.
Are we talking about this box that I created around the scale?
Yes, yeah.
No, there is no field inside. I mean, just because... Okay, let me talk a little bit about Faraday's law and the Faraday cage and consequences of electrostatics. I'll just do a real quick one here for less than a minute, Ranty. Is in electrostatics, we have one of Maxwell's equations. I know this isn't going to mean anything to you, that tells us that the divergence of the D field is 0. And the implications of this is, if I take a enclosed box, okay, it could be a sphere or it could be a cube, and it has no holes, has no seams. Now, the integral form of this thing is that the integral of d dot ds is equal to 0 on a closed surface. This is a closed surface, has no openings, has no seams. Now, if this equation is correct, which we know it to be correct, this is one of Maxwell's equations, and I construct what we call a Gaussian surface that goes through this box, then by the symmetry of the problem, in order for this to be 0, it tells us that the D field on this surface has to also be 0. You can go through the mathematics of it. The argument is that as you shrink this Gaussian surface down so that the side lengths go to 0, there's no contributions on the side, and there can be no field inside because, okay, let me back off here. The argument is this. You have a container. It's made out of a good conductor. Here are the walls of the container. We're inside the conductor here. If I construct this Gaussian surface, say this way, we know one of the properties of good conductors is a good conductor cannot support an electric field inside that conductor material, because if it did, if there were an electric field, no matter what I have, the strength of an electric field outside, no matter how strong it is or its orientation, it cannot penetrate a good conductor. And the reason for that is if the electric field was indeed, if there was an electric field inside the conductor, then there would be current flow. And we know that the movement of charges is no longer electrostatics. If you have charges moving, you're no longer in electrostatics. This can happen when you have a time-varying electric field. It can penetrate beyond the surface and penetrate the material, but for a static field, DC field, there isn't any way that you can have an electric field inside a good conductor, because if you did, there'd be current flowing, and that would be in violation of electrostatics. So if the electric field is zero, and I shrink this thing down so there's no contributions on the side, we know the electric field here is zero, then the conclusion is the D field is related to the electric field through the permittivity of the material. So I could also write this as E dot ds is equal to 0. Well, in order for this closed integral to be 0, this closed surface integral to be 0, is if there's no electric field on this surface, there's no electric field on the tangential surfaces. So in order for this to be 0, the only way that can happen is for the electric field inside to be 0. There isn't any way there can be an electric field inside when you are in a hollow cavity within a good conductor. Absolutely impossible. Can't happen. No electric field inside, regardless of what's happening to the outside world. And there's also another consequence to this. To anyone on the inside, if you somehow sneaked in here with some charge in your pocket, say charge Q, an observer outside would never know that you had this charge. Or if you moved around inside here, that it would never register to the outside world. There can be no communication between the outside world and someone sitting inside the cavity, or someone inside the cavity communicating what is happening inside to the outside world. Absolutely impossible. This is called a Faraday cage.
Okie dokie.
And so it doesn't matter what the electric field is outside, it can never ever, that information can never be communicated to the inside of a hollow cavity surrounded by a good conductor. Can't happen.
So, as the presentation was about gas laws and we were talking about pressure before, do you agree that in order to have gas pressure, we need to have walls of a container?
Repeat that again, Randy.
In order to have gas pressure, do you agree that we need to have walls of a container?
No, you can have a force field creating a artificial container, like I said, like you have for fusion reactions by creating a magnetic bottle to hold the plasma in place. Same sort of thing happens here with the Earth. You don't have to have walls of any sort of container as long as there is what we call a central force field. Within the Earth, if you have the Earth, we have a central force field that it turns out in engineering, in physics, you can show that a spherical object, homogeneous object, behaves exactly. It's indistinguishable from all the mass being concentrated at its center of mass. So I could replace this by a very small volume called the center of mass and put all the mass of the spherical Earth at that one little point, and outside of this particular diameter, the behaviors are exactly the same. So this is what we call a central force. That is, force everywhere is directed towards one point called the center of mass. This is a central force. And as long as we have a central force, which is predicted, which is given by Newton's equation, gravitational equation, gm1 times m2 divided by the separation distance squared. This is a central force. And as long as there's a central force, it can contain gas molecules outside it without having a physical barrier surrounding it.
So are you suggesting that's what's happening with the atmospheric pressure?
Yes.
So there's a force field around the Earth?
Exactly.
Okay. Right, let's see if there's any more questions. How can you do the Cavendish experiment without manipulating gravity?
Okay. Let's look at the Cavendish experiment a minute. I mean, what aspect of the Cavendish experiment? Yeah, there seems to be confusion as to what the Cavendish experiment was all about. What Cavendish did is he was trying to do what he called weigh the Earth. He was trying to determine the mass of the Earth. And in doing so, he also was able to figure out what the universal gas constant was, what we refer to as big G's. Because in order to get a value for the mass of the Earth, you have to know what big G is. So it was a consequence of his experiment. And what he did is he had this beam suspended from a thin thread with masses. This is a side view. And this was in what he called his shed. It was a brick building to keep air currents from influencing the experiment. So if we look, say, top down, at that point of attachment, we have those two masses, and then he introduced, by dropping via pulleys, other masses next to it. So there was, say, a pulley system here where he had a mass attached, and he could lower it and raise it. He's in his, say, building here. From the outside, he could lower and raise it, and it would bring it in next to the mass. So if there was some attractive forces, this beam would tend to rotate. And likewise, you'd have another mass sitting there, so it'd cause a torque and cause the thing to rotate and then oscillate. And by knowing the period of oscillation, you can go through the physics by knowing the torsion spring constant of this wire that suspends it. You can calculate what the force of attraction is, and that's what he basically did here. But to repeat the Cavendish experiment is not an easy thing to do in order to get qualitative or quantitative measurements. You can demonstrate it qualitatively, where people have done this, like in classroom demonstrations, where you have a torsion balance. This is called a torsion balance. You have a beam with two masses that's suspended by a thin wire, and you know the torsional spring constant, and you bring a mass in next to it, and you see that it begins to rotate. We call that a qualitative. It's just demonstrating the principle, but you can't get any quantitative data in which you could calculate what the forces of attraction are or what big G is. In order to do that, you have to go through all these push-ups that Cavendish did, putting in a building. And the way he viewed this thing is he had a telescope on the outside that he could peer in, so that he could stay way out away and not influence what was going on there. So in order to repeat this, you have to go through this intricate set of push-ups to ensure that your air currents are stable, that your presence is not influencing the experiment whatsoever. I've seen people trying to do these things by putting oranges or bananas on the end of 2x4s or something. It's utterly ridiculous, because the amount of forces that are experienced with anything with 10 kilogram masses are so minute. It's on the order of millionths of a Newton. And you can't possibly demonstrate it at home in your room using yardsticks with masses and any sort of crude construction. You really have to go through a lot of push-ups to construct an apparatus that is sensitive enough in order to make these sorts of measurements.
So what you've just said there, essentially, when you're talking about a crude experiment, would you agree that the Cavendish experiment, as done in the past, was a crude experiment and that it's unreliable?
The one that Cavendish did?
Yeah.
No.
Do you think
he went through a lot of push-ups? He took into account a significant number of variables and rendered them insignificant in his measurements. I mean, what you have to do in any sort of scientific experiment, you have to identify all the parameters that could possibly influence your experiment. Sometimes you don't know them all, but at least you can identify the significant ones, and you take pains to design your experiment to reduce the level of effect that these particular parameters have and how they're going to influence your experiment. You want to ensure that that amount is insignificant compared to what you're trying to measure and what you're trying to demonstrate. So Cavendish did do that successfully. And since then, you can totally forget about the Cavendish experiment. I mean, there's Cavendish type torsion balances in standards labs. You go to the National Institute of Standards and Technology in Boulder, Colorado for the United States. There's equal co-data in France. Throughout the world, there are standards labs that are constantly monitoring Big G. They have these intricate apparatuses set up using modern day technology to monitor Big G and compare them throughout these standard labs throughout the world. Britain has it, France has it, United States, Russia. They're scattered. There's about 12 primary standard labs scattered throughout the world, and they constantly make measurements on all these universal constants and compare and coordinate. And you can go to what's called CODATA, CODATA, and get the current standard values for all the universal constants, and they're given to you with the amount of uncertainty. Right now, Big G is known. It's 6.674, I think 015. I can't remember the other digits, but it's 10 to the minus 11th. And this is known to 1 part in 22,000 or 44,000. 1 in 44,000, which is 22 parts per million. So this is one of the least accurate constants that we know of today. We know a lot of our electrostatic constants out to parts per million and tenths of a part per million, whereas Big G is only known to 22 parts per million. It's an extremely hard thing to measure because of the weakness of the gravitational fields.
Okie dokie. Well, I think we've been going for long enough now. Yeah, is there anything you'd like to say? I mean, do you want to tell the audience what your qualifications are, perhaps, and then tell them where they can find you, or if there's anybody else you would like to plug, and we'll round up the show.
Yeah, I'm open to answering any questions that anyone will have. I'll remain here. I hope it's been informative and not a waste of your time, Ranty. We'll look at what the response is over the next week. If some people out there don't like listening to me, I know a lot of people don't like me. That's fine. I don't care. I just try to present the science is the best way I know how, to the best of my ability and knowledge. You can take it however you want. I don't try to get involved with the shape of the earth type debates. All I want to do is ensure that both sides represent the scientific evidence and concepts in math and physics accurately. I've corrected globers as well as non-globers on these points when I find that things aren't being stated correctly. I don't have a dog in that race. All I want to do is ensure that the concepts are presented accurately. In fact, there was one recently that I did on this Ask Professor Dave. He did a video on, it was entitled something like 10 things flat earthers get wrong or something like that. And I think it was a second or third point he was talking about the parabolic nature of curvature of the earth being wrong. Well, he's wrong on that. And I told him he was wrong. And unfortunately, he took down my comments. I've also tried to mail him directly, but I haven't had any luck on that. I'm rather disappointed at his reaction to this, but he got it all wrong. He was wrong on that. And I did a video on that as to the parabolic nature of the surface of the Earth. And the reason why you can describe the curvature of the Earth using a parabolic equation, it just depends upon how you're measuring. In one case, for the curvature formula, you're measuring with respect to a tangent and to the Earth. And in the other case, in dealing with geometric curvature, you're measuring the or developing the equation with respect to the center of the Earth. Just real quick, I'll just show you here real quick, is if you have a spherical surface and you want to talk about curvature, you're drawing a tangent to the Earth and you're looking at this drop distance down to the surface. And that can be described very accurately. This drop distance d is just 8 inches times s squared, where s is your arc length measured in miles. But you're measuring it from a tangent. That's why you're getting this parabolic nature. Whereas if you're trying to describe the surface of the sphere, it's x squared plus y squared plus z squared is equal to r squared, where this is re. This is measured from a different reference point. You're measuring with respect to the center of the Earth. So if you relate the two coordinate systems, like I did in my video, where you find the equation that takes you from the center of the Earth to the tangent line, this equation reduces to that equation. So there's no difference there. There's no mystery. It's just that you're using two different coordinate systems to describe the same thing. And when you coordinate them, you find that one is exactly the same as the other in the other coordinate system. And I'll be doing another video on this to simplify my first video. It's a little bit long and complicated, and I'm going to try to distill it down and talk about. But Professor Dave was wrong about that. And it's kind of shameful that he doesn't correct that. But that's my opinion. I just don't like it when things are misrepresented on either side.
Okay, George, would you be able to inform the audience what your qualifications are?
Yeah, oh gosh, let's see. After high school, I went to Michigan Technological University in Northern Michigan, and I studied electrical engineering. And I got my bachelor's of science degree in electrical engineering. Then I went on into the master's program in electrical engineering. And midway through my master's program, I jumped over to the math department, and I earned a master's in mathematics. And then I went back to the electrical engineering department and finished up with my master's in electrical engineering. And after that, I went to work for Hewlett-Packard in new product development. I worked in the R&D lab there for 7 years, developing new precision instrumentation. I did quite a bit design. In fact, I'm working on a video right now on one of my first voltmeter designs and what I had to go through to develop a precision piece of instrumentation. That will be coming out within the next month. And it's going to be a teaching video for engineers that are entering the field, to show them the types of things that you have to take into account to design a precision piece of the equipment. And then after Hewlett-Packard, working for Hewlett-Packard, I was out in Colorado at that time. I worked in the Loveland Instrument Division in new product development. And I quit, and I went into a PhD program at Colorado State University in electronics, and I worked with a very wonderful man there by name Budak, who was world-renowned for analog filtering theory and circuit analysis, and I worked under him for 3 to 4 years, and really honed my analysis techniques in electronics under his guidance. Very wonderful, brilliant man. And so I became more or less, since you asked, I became world renowned for my analysis techniques and my design abilities. I'm tops in my field. The fact that I happen to come on to these internet forums does not speak anything towards what my abilities are. I have another life in the professional field of instrumentation, in which I'm quite well known for my designs and analysis techniques. I've worked in standards, I've worked in new product development, and this is just kind of a curiosity for me, and has nothing to do with my professional life whatsoever. But anyway, I'm very good at what I do. So I'll just let it go at that.
Okay, thank you. Well, thank you very much, George. And there was just one last question. The force field, is it an invisible force field?
Yes. Just
Okay.
like electrostatic force field and a magnetostatic force field are invisible. We can't see them. We have to design some sort of experiment to illustrate that it's there, demonstrate it's there. Like, for example, if you want to find the invisible force field, magnetic force field about a magnet, what do? You take a sheet of paper, put it above the magnet, and then sprinkle metal filings, and you can see that the metal filings will align themselves according to the flux force field lines of flux about the magnet. You can get a visual representation of what the flux field looks like. Similarly, we can do that with electrostatic fields in a little different way by charging up non-ferromagnetic materials with a certain charge and drop them similarly on a sheet of paper and have them, these little test charge units, align themselves with the electrical lines of force. So yes, there's no way for us to visually see these invisible force fields, but we can see the results of these force fields by conducting these sorts of experiments and tests to show how small objects align themselves with these force fields.
Okay, well, thank you very much. How do I say your surname as well? It's been a bit of a topic recently because we don't know how to. I'm saying Hnatiuk. Is that even close?
That's okay, Ranty. I mean, the way most people pronounce my last name, the H is silent, and they say Hnatiuk. It's Ukrainian. The correct pronunciation in Ukrainian is Hnatiuk, but most I go with Hnatiuk, Hnatiuk, however you want. Just the H is silent. Call me Smith, George Smith.
Well, thanks for your time anyway. I do appreciate it. I'm sure the audience enjoyed it too. And I'm sure that if you check back over the next couple of days, you'll see some comments in the section afterwards. And you might even be able to follow the chat if you watch it back.
If people want to post some questions, I will check in on your video once you post it, and try to accommodate your viewers and answer their questions, via comments on your video. Now, if it turns out, I don't know how well received, like I said, this is going to be, because I know a lot of people's attitude towards me. That's fine. But if it turns out that this was helpful to anyone, I would be willing to put something together. I notice another topic of hot interest here lately has been Coriolis effects and reference frames, and I could put something together on that particular subject. It never did go over very well when I appeared on Nathan's show, as you know, because of the constant interruptions, and I could never get anywhere on that show. But I do appreciate what you've done here, Ranty, and I think you and I can work together if there's any other topics of interest that I might be able to help with. I don't know everything, but when it comes to electromagnetics, circuit theory, and a lot of mechanical problems, I am very good at it. I do know a lot, and I do know a lot about chemistry. So these disciplines pretty much cover most of the topics that I've seen discussed on a lot of these hangouts. So, like I said, I'd be willing going forward to work with you if there's any other presentations you might like, or if you don't want, just email me and tell me you've had enough of me, and we'll let it go at that. No hard feelings.
No, I'm fine. Anybody that wants to do a presentation, they can come back. They can do more presentations. It's absolutely fine. And if you're willing to do a presentation on the Coriolis effect, I would absolutely look forward to what you can do with that, because it is a hot topic.
Yeah. Well, I'll look at that. It wouldn't be something I could put together in short order. I have a lot of things going on with my business right now, but I would tend to think that I might be able to get something together by the 1st of September for you, unless somebody else wants to cover it before then.
Works for me, and I'll keep my eyes and ears open for anybody that does want to do any more presentations. They can email me at ranty@rantyflatearth.com. Well, George, thanks. Is there anything you want to say before
one
I round
of the
up?
things that I'm working on right now is I've been addressing some electric universe topics. Both Gleam and GrimV have a couple papers that they put out there, and I'm in the process of analyzing these papers. I don't know if you've looked on my channel. I've just posted another electric universe video regarding this paper by Morton Spheres, and showing I've got a challenge going out there right now to my viewers to tell me what the errors are in the paper. Next Saturday I'm going to publish a new video detailing and analyzing what the errors are in this electric universe paper, and then I will address one having to do with redshift in plasmas that GrimV has put out there. So right now I'm kind of focused on doing a final nail in the coffin to the electric universe, and then after that I'll be free up to work on Coriolis or any other topic you might be interested in.
Okay, well, thank you very much, George. People can find you by using the name that's in the description of this actual topic right now, George. I can't even say it again. George Hnatiuk. George Hnatiuk.
Just say Hnatiuk.
Hnatiuk.
N-A Chuck. Woodchuck. Hnatiuk.
And they can find you by searching on YouTube, and then in the drop-down box selecting for channel, and then you can find all your work there. So I'm going to do I'll read out the super chats, but in the meantime I'll end this call with you now. George, thanks for coming, and thanks for doing your presentation. You've been going for over 2.5 hours, so excellent performance.
Well, sorry to have taken so long here. I know it's very late for you, but sometimes I get on a roll. I'm kind of like Rumpus.
Okay, George. Well, I'll speak to you again. Okay, cheers.
All right. Take
Bye-bye.
care, Ranty. Have a good day at work tomorrow.
And you.
All right.
Okie dokie. So that was George. That was his presentation. I'm sure that he obviously may have answered a few of your questions right there and then. But I'm going to read out the super chats because there was an awful lot of super chats going through. So I don't really want to miss anybody for the comments that they left. So bear with me. I forget what I was up to. Right, okay. Please write the hand, take down this globe zombie. Rhino said keep crushing. Christopher Lee's equations are flagged. I love how you burst there. Blue Marble Wet Dream by Earth is Seriously Flat. Blue Marble can suck a D on the wine. I'm not going to read that. Earth is Seriously Flat. It caused too much trouble in the chat the last time. Tesla would be rolling his eyes, apparently, from Christopher Lee's. Space is fake, as per natural law. Big G only found in the LGBT. I won't believe in a word until I see a graph. That was to George. Right the hand is an amazing globe zombie slayer. Outer suit isn't pressurized. What's the center, George? 8 mile. Wow, there's so many I'm reading out here. George really needs a hardcore globe abortion. Earth is Seriously Flat said that. Which came first, Maths or Man by Christopher Lees? Earth is Seriously Flat says, thanks George, but Blue Marble is pseudoscience. Christopher Lees, George, my magic marker is proof. Earth is seriously flat. Be careful, he can get triggered like Brenda's Hulk. Christopher Lee's, take away his pens and he's left with nothing. You haven't done a thing, George. Shout out to Paige, I'm not your mum, says Christopher Lee's. My kids, 10 and 6, no Santa still believes in space. And finally from Christopher Lee's, push-ups equals friction. So just have a quick refresh. I think that was all of them. And for tomorrow, oh no, we do have another one actually. Moon atmos cannot be achieved on Earth again by Christopher Lee's. So tomorrow, so the offer's out there for any globe earther or series of globe earthers that want to come in and do a chit chat between themselves. I'll open up the platform around about 9 PM BST tomorrow. So I've already spoken to the Rumpus, and if he is willing to host the show kind of thing, obviously not host it, but bring in some globe earthers to have a chat, a little like the flat earth chit chats that have been going on recently, but this time from the globe earth perspective. So that's open. Whether it goes ahead or not is basically down to whether or not the globe earthers are willing to come in and have this chat. So failing that, on Wednesday we have Mark Sargent, who will be coming on. So I'm looking forward to that. We're going to have a bit of a chit chat with that. Plenty more things to look forward to as well. There's also presentations on Friday, and yeah, plenty of things to be cracking on with. So in the meantime, it is now 1:20, and I've got to be up in a little over 4.5 hours. So I'm going to round this one up. Thanks, George, for stopping by. Thanks everybody in the chat for stopping by. Thanks for all the super chats. That has blown me away. I think there must have been at least 20, so thank you very, very much for that. And yeah, thanks very much, and I'll see you all in the next one.